David Siska from Edinburgh University, and he will share with us on Fisher-Rao actor-critic gradient flow, please.
Thank you, Ranuel. So, as you can see, this is a joint work with Lukáš Pruh, my colleague in Edinburgh, and Denis Sorba, his PhD student, who is also here in the audience. So, I will talk about combining a Fisher-Rao gradient flow for the actor when solving a reinforcement learning problem with a critic, which will be a usual Euclidean gradient flow coming from linear function approximation. So you're looking for the weights in your linear function approximation. Right. Sorry, I have to figure out the clicker. Right. So the outline of the talk is I will just repeat a lot of what has already been seen, but just in case it will at least set the notation. Then I will motivate the Fisher-Rao dynamics that you will see as a limit of the mirror descent updates, and then I will introduce the actor-critic dynamics, trying to explain what some of the challenges there are, and then I will talk about the convergence. Okay, so we are working in the very usual setup. We have an agent interacting with an environment. The agent takes an action, the environment does something, creates a new state and a cost. The agent sees the new state and chooses a new action. So we have a stream of data from which we would like to learn. And when I say learn, I just mean really use the stream of data to approximate the optimal policy. I will not be talking about regret. And then in fact you will see a bit later that we are not quite at the stage where we can deal with sampling, so we'll be assuming that integrals are evaluated exactly, and sampling is sort of a problem that will come later. Right, so anyway, this is the setup. So we are working with a state space S, action space A, transition probability kernel P, cost function C, and a usual MDP, except we are looking at mixed strategies. In other words, our policies output probability distribution, and then the cost is integrated over the probability distribution, and similar for the transitions. Given state S, we choose a distribution for A, integrate, and then assume that this is giving us a new state Sn plus 1, and we add entropic regularization, which, as you've seen probably many times this week, has many nice mathematical properties, but especially in the case where you want to do Fisher-Rao type gradient flow, it's kind of if you want to talk about convergence to optimality, it's kind of essential to have the entropy regularization, and I'll come back to that. Okay, so that's the setup. I assume everyone is very, very familiar with this now. So first of all, in this setting, we have dynamic programming. In other words, if V star is my optimal value function, which I get by minimizing over all admissible policies. And for now, I mean, before you do dynamic programming, your admissible policies are a function of the entire history. And once you show dynamic programming, one of the consequences of the fact that you're working in a Markovian system is that your optimal policies can, in fact, without loss of generality, depend just on the current state. So we have dynamic programming. And for me, the main consequence of this is that because of the entropy regularization, we have this exact formula for the optimal value function. Okay, we can then, based on that, we can define the optimal Q function. But the main point is that because of the entropy regularization, I also know what the form of the optimal policy is, and I know that it's exactly e to minus Q star minus V star scaled by tau. And so if in particular you assume that your cost function is bounded, then a Q star and V star will also be bounded, and so you can, because the optimal policy is of the form that the log density is just a bounded function, which I see from this, right? I take the log, exponential is gone, and then these are just bounded. So I know that the log density is a bounded function, so I can restrict myself to looking for optimal policies of the form that have got bounded log densities. Okay, and then of course I can also define the Q function for any policy pi, and sort of few more standard consequences. I have a on-policy Bellman equation, which is a linear equation, and then from that I can get the on-policy Bellman equation for the Q function, and because of this I know it has a solution. In fact, you know, you can, the way to show that this works is you show that the Bellman operator is a contraction, but you can also define a Bellman operator for the Q function, and then not only you have a solution, but you also know that the solution is unique because the Bellman operator for the Q function is also a contraction. Okay, so that's the setup. And an important tool for analysis of all the gradient methods is this performance difference lemma, which goes back to Howard in his book from 1960. And he wasn't calling it a performance difference lemma then. For him it was just a calculation, but somehow over the years people started to appreciate how useful it is, and so sort of gave it the label lemma. And then, you know, in RL context it's been well known at least since 2002 and appreciated. And if you've not seen it before, the way to think about this guy, it gives you many things. It's as close in this setting as you're going to get to convexity. It gives you some kind of first order expansion for your value function in terms of Markovian policies. So it's just a very useful observation. And the other thing is that it sort of gives you access to the first variation of your value function with respect to policies, and you can see that as sort of policy gradient theorem for general state and action spaces. So in other words, if you calculate the directional derivative of your value function when you perturb policy pi by policy pi prime, this is the expression that you get, and basically you obtain that from the performance difference. And then, okay, if you want to sort of have a more compact notation, you can see this double integral as some kind of a pairing between bounded functions and signed measures, and then write it in this pairing, more compact pairing notation. So your first variation is basically Q minus V, which is the advantage, and then plus an extra term you get from the entropy regularization. And typically you think of this guy relative to the occupation measure created by your policy pi, and if you do that, then this change of measure terms goes away, and the first variation for the pairing with respect to that the occupation measure under policy pi is really just the advantage function Q minus V, and then the entropy term. Right, so that was all the things that I wanted to cover for the background. Apologies, I know that most of you have seen this before, but perhaps some haven't, so I didn't feel entirely like skipping this. Okay, so if we want to talk about mirror descent, it's a way of doing constraint optimization by figuring out a mapping of your your sort of control or the variable over which you're optimizing, you map it out to a space where you don't have any constraints, then you do a gradient update in that space, and then you map it back. So it's a classical optimization technique, and it goes to Nemirovsky, and again we've seen number of times that this mirror descent was mentioned over this week. And then sort of, you know, the optimization people have been working on it and started writing it in the form that we're using now. It's been extended to the space of probability measures in 2022 by Obin, Frankowski, and co-authors. Okay, and then sort of reverting back in time, in fact, mirror descent is equivalent to natural policy gradient, at least when you introduce linear function approximation. And so in the context of Markov decision problems, this has been used in Kakade's paper in 2001. Okay, so there are many ways of getting to mirror descent, but let's try to motivate it as follows. So remember, my overall objective is to find the optimal policy pi star, which comes from minimizing the value function of my MDP. And let's say, so you have an old policy and you would like to somehow utilize that knowledge and improve on the old policy. So you can start by writing the identity coming from performance difference lemma, and that itself doesn't simplify the problem in any way, because, you know, here, because of the occupation measure, the new policy over which you want to optimize enters in a nonlinear way, and here again on the KL term, it enters in a nonlinear way. But you just say, okay, we can be lazy, we can linearize, but because I've linearized and put the old policy there, I better introduce a big enough penalty so that somehow this doesn't destroy things. In particular, I would like to make sure that I choose the penalty big enough so that I'm still improving. And in fact, if you were here for Razvan's talk, you would have seen that this comes from taking the performance difference, doing certain lower upper bound calculations, and then that allows you to sort of see how big this lambda has to be compared with the problem constants, like the maximum of your costs or reward and your discount factor, etc. So that's all very nice. And then so then a mirror descent update is basically the linear term, which is your advantage or your first variation, times pi, so that's just linear in pi, and then a strictly convex term, which is KL. And if you choose lambda big enough, you have improvement, and you can show convergence of the discrete stepping, etc. Now, in this talk, I would not like to do discrete stepping. I would like to work with continuous time gradient flows, because they make certain calculations easier. And in fact, you will see that some of the calculations that I'll show you are really quite nice and easy, precisely because we're in continuous time. So let us motivate this continuous time Fisher-R flow so that it doesn't come out, that doesn't come out of nowhere at you. So if you remember the mirror descent update, it had the entropy term, and we know that if I have a linear function of measure plus an entropy term, I know the form of the optimizer. And then there is, it's proportional to e2 whatever the linear term was. Okay, and then there is some scaling that normalizing constant which you have to take into account if you want to keep to probability measures. So you can just rearrange this expression, take logs, and basically arrive at this. And you should now think of this as an Euler scheme step in the space of log densities, right? So I've got the new log density is sort of the old log density, minus the first variation and then minus some constant, and 1 over lambda will be my step size. So if I send lambda to infinity, I'm sending my step size to 0, and so I would at least formally expect to get this kind of gradient flow, and that's, you know, that's the gradient flow for log densities. And I mean, you can show that this has solution under assumptions, sort of bounded cost, etc. That you know, the setup that we've seen before, you can prove that this has a solution. You can also show that it's equivalent to the flow on the space of measures just through, you know, observing that this I can write as a derivative of log through this simple calculation. And so I kind of have, okay, derivative of log is this, and I know what this is from this side. So I now have a flow in the space of measures. Once I rearrange it, I can write it in this tidier form by multiplying through by this density. Okay, so this is now the gradient flow we'll be using in our coupled actor-critic. We'll be using this for the actor. Here for now I have the exact first variation or the exact advantage. So if you've got the Fisher-Rao flow with the exact advantage, you can prove the chain rule, and then you apply chain rule, and you very easily get policy improvement. And in fact, if everything is sort of, once you've proved that everything is nice, with the exact updates, you can also get convergence, and the calculation is very simple. So you treat your KL integrated against the occupation measure created by the optimal policy. You treat it as let's say Lyapunov function or the object from which you want to get convergence, and then you take the time derivative of this object. So the time here is pi t coming from the Fisher-Rao flow, which I write in this way. And then okay, it's just a calculation. You write what KL is. This guy is from the pi star, doesn't depend on t, so the time derivative will kill it. This guy now is exactly what I have for the Fisher-Rao flow. So this is what I put there. Then okay, I know that this has the right hand side that I want. And then because V pi t satisfies the on-policy Bellman equation, I know that the flat derivative or the first variation integrated against pi t, so against its own measure, integrates to 0. So even though it's not here I can just add it because it integrates to 0. And then I get to this. And this, you see, this is just performance difference. So I now substitute from this, I substitute the one term, another term that comes from performance difference. I get something that looks like this. You solve it and move things around, and you get exponential convergence. So it's the simplest calculation in the world. Of course, you have to check that all the manipulations are valid, but that can be done. And now one thing I would like to point out is that on the right hand side, the error term, okay, you've got a nice exponential, part, but there is the KL, which is of the form pi star to pi 0. And we know that because we've added the entropy regularization, you can you see that your pi star has full support, and then so to make use of this estimate, or you just say, okay, my initial initial distribution, I just take pi 0 to also have full support, and then I expect this KL term to be finite. And you might be thinking, okay, so what would happen if I got rid of the entropy regularization? So getting rid of the entropy regularization would at least formally mean that I am sending tau to 0 in this expression, and if you do that, hopefully 1 over t will come out. So you say, okay, if I send entropy to 0, I've lost something on the rate of convergence, but otherwise it's okay. But then it depends on what your action space is, because if your action space is finite, then you can get a uniform band on the KL term, which just depends on the log of the number of entries in your action space. And so then you have a finite term and 1 over t, and it's fine, and sort of you say, I didn't need the entropy regularization, or I kept the entropy regularization to accelerate convergence. Not so important. If your action space is continuum, then we sort of know that for many problems, if you don't entropy regularize, your optimal distribution is supported on Dirac's, right? I mean, that also goes back to Roxana's talk, where when she was talking about strict stopping rules, they were just strict stopping times. They wouldn't have had full support. Same thing. So at that point, it's really not clear how to choose your initial measure, right? Because you either pick something which has got exactly the support on the same Dirac's, or maybe fewer more Dirac's, but you have to pick them out correctly. Otherwise, the KL term will be infinite, and this estimate will not give you anything. So somehow, if you want to talk about convergence to optimum, having the entropy regularization is important. Okay, so this was the actor. Nice and easy. If you have exact updates, you get exponential convergence. So now we want to add the critic, and let's see where we get to. So, bit of overview. So, actor-critic algorithms have been considered for a long time. So there are articles that consider tabular setting, show convergence. This one is with linear function approximation and actually stochastic sampling. They show convergence to local minima, in other words, to points where the gradient becomes 0. And then there has been quite some work, sort of these 3 papers that use linear function approximation, discrete state and action spaces, and no regularization. This one adds, this one allows, sorry, I don't know why I've got it here now, that's some kind of, because of the linear function approximation. So this one doesn't have discrete state and action spaces, but they use kind of a linear function approximation. They use Fisher-Rao dynamics for the actor, and then critic is a mean field approximation of one hidden layer network. So what that means is you still have a linear function approximation. Now your critic flow is in the space of probability measures. Okay, but in fact the result is strange to interpret. Doesn't use convexity of the critic. It uses restarting for stability. So whenever the critic goes too far away from initialization, they just restart it. It's really not very clear to where it converges, and they use the KL as the gizmo, like in the previous slide, through which they want to get convergence, but they add no regularization. So in principle, the KL term can be infinite. Or well, maybe that's why I put it with discrete actions, because the only way to get this finite is to have discrete actions. Okay, and then there is a paper which uses discrete states and actions and entropy regularization and proves convergence. So our focus is on entropy regularized MDPs for general state and action spaces, in particular general action spaces. And hopefully I've convinced you that we sort of want the entropy regularization there. Later you will see that in fact the entropy regularization is what gives the biggest headache for stability, but let's get to that in a moment. Okay, so what are our assumptions? So we are going to work with linear function approximations. So phi will be some basis functions which, given SNA, will output an out number, and we will, without loss of generality, assume that this is Euclidean norm in Rn, that their Euclidean norm is less than 1, because your parameters, when you're making the linear combination, can always scale them. And then we'll work under this Q-pi realizability assumptions, which again we've seen a number of times this week. And okay, so when would you expect something like this hold? Well, there is the trivial tabular case where you say, okay, my basis functions are just the canonical basis of my S cross A table, if you like. And then the other situation where this is satisfied is the case of linear MDPs, and you have seen them, for example, in Lina's talk. Okay, so that's the assumption on the problem and the basis. And now we would like to, okay, introduce one more assumption. So we're assuming that if I look at this sort of at this matrix formed by the basis functions integrated against the initial state action distribution, then this will have a positive smallest eigenvalue. And because, as I mentioned, we won't be sampling, we'll be assuming that all the integrals are evaluated exactly. This is sort of this is a term that will appear and will allow us to get convergence relatively easily. And then, okay, you probably already saw the state occupancy kernel. In a similar fashion, we can form the state action occupancy kernel, and then we can think of the state occupancy kernel with respect to some distribution beta, which would be our initial state action distribution, and that's just an integral over this guy. Okay, so we will be approximating the Q function through our basis function, so that's just a node now. QSA with theta is notation for the approximate Q function, and this will then be our approximation for the first variation, which we will use in our actor dynamics. So what about the critic? So for the critic, we first look at this Bellman error. In other words, we are saying, okay, I want the Q function to be a solution of the fixed point problem under the Bellman operator, which was capital T, which we've seen, and then I know that if this guy has full support, well then the first entry in the state action occupation measure is just beta, so whatever happens later somehow doesn't matter. So as long as I can choose the initial state action occupation measure with full support, then this mean squared Bellman error identifies the correct Q functions. So now we are saying, okay, we want to have a gradient flow for the parameters, so maybe we would somehow want to take the derivative in, sorry, mixed up with this, of this mean squared Bellman error with respect to theta, but in fact this is not what is done. And one of the reasons is that if we were to do that naively, we would get, you know, we can calculate the expression, but then you're taking the gradient here, and I have this, and then eventually when you get to thinking about what happens when you're working with samples, you know, this will just be creating additional variance in your algorithm. So in fact, what is done in practice is that instead of working with this gradient on the mean squared Bellman error, you work with this semi-gradient, which is defined exactly as this, and the way to see it is, well, basically, I don't want this guy there because it will be high variance, so I just drop it, and okay, you just drop something that doesn't look very convincing, but in fact, it can be shown that sort of the relevant, you know, monotonicity property, if you think of it that way, will be maintained by the semi-gradient, in the sense that you can connect it to this loss L, which is just loss on the sort of directly on the Q function, even skipping the Bellman operator. So now, what am I doing for time? I'm slow. So we've done just the actor dynamics on its own without any approximation. Let's just do just the critic dynamics on its own without updating the actor. In other words, I fix pi. I know through my Q pi realizability assumption that there will be theta for which I have this, and I want to find this theta pi with this semi-gradient flow. So does that work? Well, I look at the difference along the flow to the thing that I'm looking for. I calculate with chain rule. I then use the lemma on the previous slide, which connects it to the loss function. I write out what things are, and I see that the matrix for which I have a minimum eigenvalue condition appears. So I use that, and I get a nice expression which I can plug it into Grunwald's lemma, and I see that this will indeed, so this semi-gradient flow is perfectly good at sort of solving, at finding the parameters for a Q function for a given policy pi. So far so promising. But it kind of it explains why you need some kind of an assumption on the minimum eigenvalue, because without this you can't even talk about finding a Q function for a fixed policy, let alone the optimal policy. Okay, so I think I will not go through any more calculations in detail. I will just now cover the results. So remember what we've done so far. We said, well, we've got mirror descent. For the mirror descent, I've got this continuous time idealization in terms of Fisher-Rao dynamics. This is still written with the exact first variation advantage function. I replace it with the approximation. So approximate first variation coming from the Q function, which I'll be learning. And now I create this coupled dynamics. So this we've already seen, except now the target's moving. And here I've got the actor dynamics. And the key to making this whole thing working is that you have to work with two time scales, and quite naturally you have to run the critic dynamics faster if you want to see the convergence to the optimum. In other words, you will have to allow time for the critic to be sufficiently good critic before sort of moving too fast with your actor updates. Okay, and then the key to the analysis is getting stability of your flows, because then once you have stability, you could also argue that this is how you would get existence for the coupled dynamics. So the first one is that your parameters for the critic are kind of, you know, they are behaving with something that looks good. This would, if I had just this term, this would through Gronvold give me exponential decay to 0. But then there are the terms which are coming from the KL, which I have to control to be able to conclude anything. So, but okay, you know, if tau was 0, let's say, then this would already be okay. I would have stability of the parameters for the critic. Calculation I skip. And then on the other hand, you can look at the stability sort of for the supremum over all states of your KL divergence. And for that you can prove an estimate of this form, and then eventually you can bootstrap the two together to get, first of all, that you've got no finite time blow up of the KL, and moreover, if you make the critic run very much faster, exponentially faster than the actor, then you also get no finite time blow up for the critic. Okay, I'm skipping the calculation, and then, you know, similar to the calculation you've seen before, just tracking the error, which now basically says, well, how good is the critic that I've got along the flow against the values for the that would be the exact values for the Q function. So this is how you're accumulating the error, and so you need to handle this term. And if you choose your critic again to be your critic flow to have an exponentially faster time scale, then you can get overall convergence, of course under the assumption that you're not evaluating things from samples, but you're evaluating integrals exactly. So if you ask what's this got to do with RL, you could say nothing, right? We're doing a continuous time flow, which is not an algorithm, and we're pretending that we're evaluating integrals exactly. On the other hand, if you couldn't get a result like this, then you'd probably be thinking, well, what hope do I have in discrete time? And once I throw sample, you know, the errors arising from estimating integrals into the mix. Okay, so that's that. So a very quick summary. We've got actor-critic dynamics with an inexact first variation for the actor, semi-gradient for the critic, exponentially faster dynamics for the critic, and we get a convergence. We need a bunch of assumptions, you've seen them. What else? Sort of the natural things. Discrete time stepping, Dennis I think pretty much has got a result there. And then thinking about Monte Carlo approximation errors or sample complexity, that's much more work. And then maybe eventually regret analysis, so that you have sort of a complete picture. Okay, and then because I am the last speaker of this workshop, I have the pleasure of thanking all the organizers. So in no particular order, Ren Yuan, Yufei, Sam, and Lukáš, who is not here. And I would also like to thank the I&I staff, whose names I don't remember from the top of my head, but they're numerous. So thank you, and I hope you join me in thanking all of these people who made this event possible.
Do we have questions about the talk?
Yes, yes.
In discrete actor-critic, usually when you demonstrate global convergence, you would need sometimes two-time scale stepsize choices.
Sorry, I would need?
You need two-time scale step size so that step size gets a separation.
Yes.
In continuous time, this is not the case.
Well, you sort of see that you're increasing the speed of the critic exponentially. So in fact, in the equivalent in discrete time is that you basically, you know, I'm not doing one update of I'm not doing one-step update of the actor and one-step update of the critic. In fact, you need to do one step for each step update of the actor. You need to do multiple update steps of the critic, and the number actually increases with the actor iteration index, and that's how you sort of mimic this exponential time increase.
But
So
there are some work in discrete case showing that under certain proper assumptions, you don't need to have such a separation. Like you can use single time scale algorithm. So what does it correspond to in this case?
In the continuous case, it would correspond to just, okay, so taking a step back, what is making this thing, where this sort of exponential increase comes from is that you're working with continuous action space where the entropy term can become unbounded. And you have to handle that. So if you were to roll back and you say, I just have a finite action space, I have a uniform bound on the entropy, I wouldn't need this exponential increase. I would just put it should be enough to just have a constant. I just have to sort of run faster, but with a number that doesn't change along the flow. Thank you for the question. I should have explained that earlier. Thank you.
So actually you answered my question now. So I was thinking like when the action is finite, then you might not need the chaos term to come
Yeah.
in. Yeah, so you just answered.
No, thank you. Boris?
Could you say a bit more about the linearization part and the challenges without, because from what I gather you're relying on that being a good approximation, or?
Oh, well then it's, I mean, okay, so two things you can, where do we introduce the linearization? Oh, here, QPy realizability. Okay, so few ways to generalize this. One of them is you say, okay, I don't have finitely many, I have infinitely many. That sort of, you know, and then then the assumption becomes, let's say, less restrictive because you're covering whole Fourier bases, yada yada. Still linear. The mathematics is a bit more tedious, but basically things should still work. The other thing you can do is you say, okay, I have finitely many, so then sort of this is not exact. I am, you know, I'm carrying some kind of approximation error with me, and I look at how it accumulates. Sam?
Are your quantifiers in the right order in that assumption? Because it looks like data can depend on SNA.
No, I'm not.
Okay. So you're saying that I need to be able to approximate linearly globally?
Yes, sorry
Okay.
about that.
Okay.
Yeah. Otherwise, it's, yeah.
Trivial.
Yes. I apologize. Yeah, so you can then say, okay, it's not exact, I carry around an error, and that in fact is not so, in some sense, not so exciting, because you would get to sort of this point and you would say, well, okay, one part of this I'm handling because some of it is approximated well, and then there is another term which is sort of accumulating another error which comes from what I've not approximated. And then, of course, if you want to go to the really interesting cases, which is what happens when you put neural networks there, which is what actually people do in practice, then, well, let's figure out supervised learning first.
If no other questions, let's thank David for the very